No. Hello and welcome back to Calculus 1, section 311 on related rates. This is part 2. The stream was dead yesterday. Let's see if it works today. So related rates is a formula such as, let's say, this one here, which connects at least two rates which are two different derivatives that measure rate of change of something. In this case, we have rate of change of volume and rate of change of the edge of the cube. In one of the next examples, we had here the rate of change of area in respect to time and the rate of change of radius in respect to time. That was another one. Here's another formula we did. We had two airplanes approach each other at 90 degrees, and we calculated the rate of change of speed between the two airplanes going closer to each other. So those are all problems that we did. I promised a few more problems for today so we can practice this. And again, by far, this is my favorite Calc 1 section because it's applied and it's really cool. And let's take a look at something else. Say you have okay, here is ground. Now we're going to draw a house. Obviously every house needs to have a chimney somewhere, right? And here is the gutter. Right, so that's that. Now what you do is set up a ladder, and then someone climbs on that ladder. I'll put the hard hat right there. To clean the leaves outside of this gutter. This person is clearly not me, it's way too thin, but it's okay. So, what's the situation? Well, someone else is passing by this point, right? And that's one of the good old, right, kick at the ladder. Now, when this point goes this way, this is obviously distance x, and this is dx dt. So as you kick out this side of the ladder should go down, which is the distance y at the speed dy dx. Now let's say that the ladder is how many feet tall? 10. 10 feet tall ladder. And we can actually use this information to figure some of the stuff out. So x can be, let's say, I don't know, 3 feet away from the house. And you kick out the ladder at what speed? How about 2 feet per second? Sure. So how fast would this person fall? How fast will this person fall. That translates into dy dt equals question mark, because that's the speed of top of the letter going down. Does this make sense? Perfect.
Yeah.
So remember what I asked you to do before. I asked you to think about geometry,
Yeah.
and then formula. So what's the geometry? Right triangle. And what's the formula? Pythagorean theorem. So x squared plus y squared equals to ladder squared. So every problem should start this way. You understand situation because it's something that you, well, hopefully you don't get to relive this one, but something that you can live through. And then
My uncle had this happen once. He was laid up for...
somehow I have the sense that you were the one who kicked out the bottom.
there.
You were, oh, okay. But you thought of it. That counts.
I don't think so.
So this is what we have, and we start by taking the derivative, but there is a very important feature of this problem that you need to consider, and that feature is that, I'll write it in blood, L is a constant. L equals 10. See, the length of the ladder is not going to change no matter where the ladder is. Look at the previous problem with airplanes. X distance and Y distance are both changing as the airplanes are closer to the airport. And as airplanes are approaching the airport, the distance between two airplanes is also changing. So this capital D was also a variable, and we had to differentiate that variable, which is why we had the term where we differentiated D and got dd dt. Now the new problem, ladder is always 10 feet tall. No matter which way you put the ladder, it's always going to be 10 feet long, 10 feet tall, whatever. And even when it's on the ground, it's just going to be 10 feet tall. So our formula now is not L squared, our formula is equal to 100. Because it's constant. And when I take the derivative in respect to time, that number is going to go to 0. Previous problem with the triangle gave us all of these values. So now this becomes 2x dx dt plus 2y dy dt equal to 0. We divide by 2, and we have x dx dt plus y dy dt equal to 0. So x is 3. Dx dt is, what's dx dt is 3? No, dx dt is 2. Y we need to figure out, so we'll use x squared plus y squared equals to 100. And finally, dy dt is what we are looking for, so we leave that as the unknown. So I have to work out this formula. X squared, x was 3, right? Yep, x is 3. So that's 9 plus y squared is equal to 100. Y squared is equal to 91. Y is equal to plus minus square root of 91. and we are not using positive value. So we are going to, we only use the positive one, exactly. So square root of 91 is going to be 9.5 and that's that. So now we have everything. 3, which is the distance in x, times 2 plus 9.5 times dy dx. Now I need to worry about all of those signs which we said we have to worry about. So what are going to be negatives? You have speed to the left, so that's going to be negative. So that's negative 2 over here. Downward motion, so that's negative dy dx. So if you multiply the whole equation by negative 1, they just, all of the negatives go away. So I have 6 plus 9.5 dy dx is equal to 0, and dy dx is equal to negative 6 divided by 9.5, which is going to give us negative 0.63 feet per second. And that's negative, which is good because, as you can see, it's going downwards, right? So the speed at which the person on the ladder is going to fall is negative 0.63 feet per second. That's like a leaf falling over that. It's not a big deal. But then, considering how thin, right, this person is, I mean,
I see.
right?
How do we get positive 6
Like,
multiplying 3 by negative 2?
there is a negative 1 over here, which killed all the negative signs.
Where did that come from?
I just multiply the whole equation by it.
Okay.
All right, let's design something for SpaceX. Yeah. So we have a launch pad. And on this launch pad, here's the launch pad. It's like, that's launch pad, right? Look at that design, awesome. We're going to put a SpaceX rocket over here. You know what? I'm gonna start my own space program.
What would you call it?
Nix.
Nix?
Yeah. There you go. Very original. Very original. So what are you going to do? So as I am starting this revolutionary program, I want to record and put these videos on YouTube because it's cool and I need to design. This is a very sophisticated camera over here. It's a tripod for it. Now over here, this red hinge is going to have a servo motor in it that will rotate the camera with the angular velocity omega, for those of you who love physics. And the reason for it is I want my rocket to always be in the middle of the shot. So I want to figure out the mathematical formula that will be updated real time, which will produce values that will be sent to the not the sensor, they would be sent to the servo motor, which will turn the camera. So this camera has the viewing angle of whatever the viewing angle is. So I'm just going to draw the straight line for the middle of that viewing angle, and then as the rocket goes up forever, right, there will be an angle theta for which the camera is going to rotate at each instance in time, so that the rocket, which is this is the target, the X from the Nix, all right? So that that X is always in the middle of the shot. Now, the rocket is going to shoot straight up, obviously. So it's going to have the height of the rocket. We can put the camera, let's say, 500 feet away. 1,000 feet away. Okay, 1,000. 1,000 feet. And we're just going to shoot this straight up. So my question is to find this omega, the angular velocity. Angular velocity. So how we get that? Well, we start from first realizing geometry, and then formula. What is the geometry of this problem? It's a right triangle.
Oh, I was looking at the part of the angular velocity by mistake.
And which formula we get to use now? Tangent x, nice. Well, let's just put tangent x. Because we have an angle theta, and we have opposite, which is h, and adjacent, which is 1,000. So we're going to use, not tangent x, tangent theta. There we go. So we write our formula. Tangent theta is equal to h over 1,000. Good. Then we differentiate this formula in respect to time. Clearly, theta is changing and height of the rocket is changing. So now when I take the derivative, what's the derivative of tangent? Yes.
Secant squared.
Secant squared, great. Secant squared theta, followed by d theta dt, because we have the chain rule there kicking in, equals to, what's the derivative of h? 1. So 1 over 1,000 times 1 times dh dt. Well, this is already related rates, but we can actually clear it up a little bit. So, wait, what's what here? What is this d theta dt?
That's the
Change of the angle over time.
Yeah, what is that?
Angular velocity.
That's angular velocity. Because the swiping the angle in time is crossing that distance in time. So, right, d theta dt is your omega, angular velocity. So that's what we're looking for. Ha! I got it in a formula. Awesome. And what's dh dt? Which is what? Rocket's velocity. Excellent. We have a rocket scientist here. I love it. Speed of the rocket. Nice. So let's go and kick secant to the other side because we are looking for d theta dt. So d theta dt. Guys, let me write angular velocity equals how fast the camera is turning.
Yeah.
So that's the concept. That's the concept that we are after. So d theta dt is equal to 1 over 1000 secant squared theta dh dt. Now secant squared in the denominator becomes what in the numerator? Cosine squared. Very good. So cosine squared theta over 1000 times dh dt. Secant is 1 over cosine.
Yeah.
So now we take a look at the, because we don't really have an angle as an input. So we need to transform this cosine into the labels we have. So cosine is adjacent over hypotenuse. I don't have the hypotenuse yet, but we can use the Pythagorean theorem to find that this is 1000 squared plus h squared. That's the length of the hypotenuse. So now the cosine squared d theta dt is going to be square root of 1000 squared plus h squared, everything squared because cosine was squared, over 1000 times dh dt. So it simplifies nicely into omega equals d theta dt, which is 1000 squared plus height squared divided by 1000
I'm sorry, I'm not
dh dt.
trouble following all of this.
So this is what you plug into your controller. What are the only two variables that you have as input? The height of the rocket and the speed of the rocket. And those two are known at all times. If you ever watched the SpaceX launch on YouTube, those are given in the right-hand corner of your of the web stream. Doesn't matter which one you watch, they all have it. Yes?
This is quite a stupid question, but why did you replace the cosine with the hypotenuse? Like, why did you say without the square root of 1000 squared plus h squared squared?
Oh, wait, it was supposed to be over hypotenuse. Because
Well, it's supposed to be adjacent over hypotenuse.
yeah, adjacent over hypotenuse. Yes. I'll fix that.
Oh,
Let me just, oh my, come on, the entire college doesn't have ad block. We have to sit through all of this nonsense so we can. Yeah, I have to fix. I have to fix this problem. It's not correct. Because instead of the entire cosine, I placed only part of it. So we'll have to fix the last two lines. The cosine is adjacent, which is 1000 divided by the square root of 1000 squared plus h squared. And then we have the h dt.
You have to like square the whole.
And yes, we square the whole thing because cosine was squared. Good. So now the whole bunch of stuff is going to cancel.
This is equal to cosine theta.
Yeah, that's cosine theta is replaced by the square root. So now d theta dt, we have our
Yeah.
1000 squared divided by 1000 times 1000 squared plus h squared, because the square root canceled, dh dt. And now 1000 kills the square over here. So the formula that we were after is omega is equal to d theta dt, 1000 over 1000 squared plus h squared dh dt. That's the formula we were after. So now this is the height, and that's the speed, and both of those are known in the mission control, so you can feed those two numbers into the control. You have the formula programmed in the controller, and it computes the speed at which it needs to rotate the camera. The camera needs to rotate. You can't just put any speed, because the rocket is going to shoot and speed up. So when the rocket is close, right? The rocket is close to the camera. The camera needs to spin faster up, and then when the rocket is really far away from the camera, then the camera will turn very, very slowly. So you have to actually use the formula. You can't just say, oh, let me calculate one instance and then use that speed for the entire launch, because it doesn't work that way. The rocket will be picking up speed, but also the rocket will be moving away from the camera too fast, and the further away the rocket is from the camera, the less camera needs to turn to right. It's just like, look through the window, you can see 100 trees over there.
I can.
Okay, well, everyone else, look at the trees over there, and you see 100 trees, right?
See it over here?
But now,
Oh, I see
if you are sitting, if you are close to the trees, you can see one or two trees, right? So that's the idea of this objects being far away. You don't have to trace them with a great right, with moving your eyes too much. So you just move a little bit from one tree to another. But if the trees are right in front of you, you have to turn. So that's the idea. And as you can see, you have the right triangle, but now this time in right triangle we use the trig. So we had 3 right triangle examples, and each one was different. In the first one, right triangle, the distance d between the airplane was diminishing, so d was a variable. In the next example, the length of the ladder never changes, so hypotenuse never changes, and it was still Pythagorean theorem, but it was different type of a problem because we had L to be stuck at 10 feet. So the problem worked out a little bit different. And now we again have the right triangle problem, but this time around we have a trigonometry problem because there was an angle involved, and we were interested at how fast the angle is changing, which is our omega. Now all of these problems, with exception of the latter one, were similar in a sense that anytime you put a variable letter down on your picture, it was always a variable, except the length of the letter where it was constant. So now you have this thing to worry about. So here is another example where this is very important, and then we'll finish. So 2 more examples. This example here is the example of a soda can.
You gonna get trash?
No. Sorry for disappointment. So you have a soda can over here, and you are going to put the straw into the soda can and take a sip, right? Take a sip of the drink. Now, in some of the projects, sometimes I actually have this for a project. You can Google the size of average sip, actually, and then you can do calculations. If you don't believe me, just go ahead, Google it now. You'll see. So if you look at the can, right, the amount of liquid inside is the volume of the can, and the more you drink, the level of liquid goes down, decreasing the amount of drink that you have. Now, you can Google the size of the can as well in inches or centimeters, and that's something that it's also standard and known. So just for the hell of it, let's say that the radius R is 2 inch. 2 inch. The height of the can is, let's say, 8 inch. And you want to see what is the dV dt, which is, no, sorry, the h dt, the change in height of the liquid if you are drinking, which is dV dt, right? Change in volume. As you drink, you are reducing the volume. So dV dt, and that's going to be some kind of negative number, obviously, because you are subtracting the liquid from it. Now, you looked up the size of the sip, and what did you come up with?
It says that it's around 16 milliliters.
16 milliliters. Oh, great. I gave all this in inches.
You can change it to
Or 16 centimeters. 16 cubic
So,
centimeters.
how about you change that into inches cubed in the Google conversion over there? So 16, you said 16 milliliters?
Yeah.
So 16 milliliters to inches cubed.
It says 0.976 cubic inches.
Okay, so we'll call that 1 inches cubed. Thank you. Because you said 0.97, right?
Yeah.
0.97, that's good enough to be 1. So you get to drink in one average sip about 1 cube inch of Now, see, you research this kind of stuff because it's fun, right? Next time someone tells you, what do you know? Like, do you know? Please remember it's 0.97. That's much better than just 1. All right, so now we have this, and we have the formula for the volume of the cylinder. Yes?
Wait, is that the second that's higher than?
Yes. Negative 1 inch cubed per second, yes, because it's per time. Volume formula is base times height. Base is a circle, so that's r squared pi, and then times the height. Now, let me write it here. Before we differentiate, we must separate variables from constants. Because remember, if you're differentiating constant alone, it goes to 0. If you're differentiable constant within a term, it gets copied. If you're differentiating a variable, it's going to get its dt chain rule. So, is volume a variable? You ask yourself, is it something that is changing in this scenario? Is volume a variable? Yes. As you're drinking, you have less volume of liquid. So, it is a variable. Is the radius a variable? No. See, the can is always 4 inches wide, which is diameter. So radius is half of that. So radius is not a variable. So that's going to be a constant. In this case, you get to copy it. And then is height a variable of the liquid? No. Yes, right? Height is a variable because it's going down as you drink. So variables are volume and height, and radius is a constant. So now we can take the derivative with these things in mind. R squared pi, no, we're going to plug in for r squared because that's not going to change. So that's 4 pi h. Whatever is not a variable, you can immediately plug into the problem and do it. So dv dt is equal to 4 pi dh dt. So now you know that dv dt is negative 1, 4 pi dh dt, and dh dt is going to be negative 1 over 4 pi inches per second. You can go get the decimals if you care. So in this particular case, because it's a cylinder, right, it's a can, the radius of the can doesn't change, which means the radius of the liquid that occupies that can does not change. Radius is always 2, and because radius is always 2, there is no change in radius, so it's not a variable, it's not a, we are not going to be differentiating that one. The change in volume is the amount of liquid that you drink, which is the size of a sip, which you kindly looked up for us. So we are able to calculate exactly the change in height of the liquid in the can. So next time you're out with your friends, as they drink from the can, you just go, by the way, do you know? And that leads into all of this. Work it out on a napkin. the last problem for today, we're going to have a conveyor belt with some stuff on it. Can be corn, can be gravel, I don't care what it is. It's going to fall onto a pile. And what geometry forms as the stuff falls on a pile?
Makes me think of LM.
I said, what geometry is forming? What shape? What? As the gravel or sand or corn or whatever it is. The cone, thank you. Holy nightmare, come on. It's the cone. So it's going to fall and it's going to create a cone. And then, in time, the size of the cone is going to grow. The amount of stuff coming in is clearly the change of volume, because the volume, the size of the cone is getting larger. If you send more stuff down the conveyor belt, the cone is going to grow faster. If you send less stuff down the conveyor belt, it's going to go slower. If you don't send anything, it's not going to grow at all because there's no new stuff coming in. So whatever is getting off of the conveyor belt and is falling down onto the pile is your dV/dt, because it's changing the volume in time. And you can adjust that by whatever means you have on the other end of the conveyor belt. Now, we have geometry is cone, and formula is the volume. Volume for the cone is 1/3 pi r squared h. Because the volume formulas are always base, area of the base times height. Well, the base is a circle and the height is h. But since this is what I call a spiky object, you have 1/3 in front. And we are going to generalize after this all of the volume formulas, so it's going to be easy for you to get those. So volume formula is this. Remember what we need to do before we differentiate. We have to sit there and think hard. What are the variables and what are the constants? Is volume a variable or a constant? Variable. Why? Because the size of the cone is changing, it's growing, right? So volume is a variable. Is radius a variable or constant? As you move, it's a variable, because if you take this middle line here, you can also see that radius is growing, because the cone gets fatter as the time goes on. If it's fatter, that means the radius is growing. And how about the height? Also a variable, because the height of the cone grows as well. See, these are the important notes to put down, because this type of analysis is situational, right? You in some cases, a previous problem, our radius was constant. This problem, radius is not constant. So it depends on the geometry of the problem. Now, does it mean that the radius is always going to be a constant in every cylinder?
No.
No, because if I turn the cylinder on the side and I cut, let's say you take a barrel and you turn it on the side and you cut it, right? You get 2/2 of a barrel, turn it this way and you cut on the side. And you have 2/2 now, and you can put stuff to feed the animals from it, right? Now, if you take a look at this side, the radius is constant for the semicircle that you have, but across is not constant anymore. But then this one became constant, but the height going down, that problem is much more interesting than what we had earlier. So those of you that want to do these advanced exercises, they're in the book and they're a lot of fun. So now, we have a formula which has three variables: volume, radius, and height. Now look at this, it's r squared times h. As I differentiate,
Yeah.
what happens as I differentiate?
So you're gonna have to do product rule.
Yes. So we have pi over 3 r squared h, and as I differentiate, we have to do product rule because it's right, two functions multiplied. So dv dt, change of volume in time. What kind of volume? The volume of the cone is going to be, we copy pi over 3, that's constant, and now over here in parentheses, we say copy the first, r squared, the derivative of h is dh dt, plus copy the second, which is h, and then times derivative of r squared, 2r dr dt. So finally, we have our formula. And as you can see, this formula is far more complicated than the formula we had earlier.
That's a HDR. I can't tell what that value is. Is that a 2?
Yeah, r squared is 2r, right?
Alright.
Good. So here's your related rates. And as you can see, you have the change in height and you have the r dt. Now, for most part, right, we are interested in figuring out the formula and then you just have the numbers and you plug them in. Now, this problem is more interesting than the previous problems because you have to have an additional thing to worry about. Because now you have three rates. And usually you don't have all of the rates given. So you have to figure out, using more geometry, you have to figure out how to change either dh dt into dr dt or other way around. And that is done through similar triangles. So when you have your, we'll just take a half of your cone. When you have the cone grow,
That's related rate? I can't see that.
related rates.
Related.
Yeah, you gotta sit closer if you can't see from there. So we have the related, we have now the cone, which used to be this large, and then as the time went on, the cone is, by the way, this is a cross section, right? This is the cross section, right? So the cone is here, but then we just look at the half of it. We don't need to look at the whole thing. So this is your height, and this is your radius. So if this is the height that is changing, and that's the radius that is changing, and then you have the full radius when you measure this, I don't know, let's say 10, and this one was 30, whatever. You can write the proportion, what age is to 30, r is to 10. So that's a basic proportion from algebra. And you can solve for, let's say, age, because that will be, when 30 goes to the other side, will go up. 30 divided by 10 is 3. I can write it. 30r over 10, which is 3r. So now we know that age is 3r.
I assume that, well, I think I know what radius would be then.
Well, they are changing, so we just know the relationship between them.
Good.
And once we have this, we can differentiate this in time to see how they change in relationship to each other, which gives you dh dt is equal to 3 dr dt. And this is what you can also plug in to eliminate one of the variables. So let me go blue. Plug in to eliminate one of the variables. One of the rates, how about that? So if you don't have both rates given, you have one or the other, you can always convert one rate into the other rate and eliminate the rate you don't have. So if all the rates are given to you, well, you will obviously just plug everything in the formula there and be done. But if you are missing one of the rates, then you can look at the rest of the geometry of the problem, work out the proportion, and then at the end you have the relationship between two rates and you can replace one of the rates. Now this kind of manipulation now is a little bit more advanced, obviously, because we are dealing with connecting variables together and then creating additional rate. We did this on a basic level in every problem we had so far. Let's say in this triangle problem here, we had to calculate on a side the hypotenuse so we can convert the cosine. In this particular problem here, we had to work out this part here, which is to find the unknown value for y so that we can again replace the variable that we did not have. In a problem before that, we also had to work a Pythagorean theorem, which was worked out here, to find distance d, which we did not have. So pretty much in every one of these problems, you had to do a calculation on a side to get rid of the one of the variables that you actually don't have. Obviously, these very basic problems like this, they only have two rates and so on. In some of those, you don't have to do it, like the SIP one. Now, how interesting do these problems get? They get very interesting. And some of these problems, as a student, I spent a very long time trying to figure it out. Right? So basically, the vanilla problems are going to be in a textbook on the first page of your homework. But all of the stuff that it's actually worthwhile figuring out, because you might be actually making money with it later on in life, all of those problems are towards the back. I remember investing like an hour or two working out a Ferris wheel problem, and then there's the movie theater to set up the home theater. That one I actually used to set up the stuff in my house, but the Ferris wheel one was very interesting, and you can find it on in your textbook. That one took me a long time to figure out formulas and which way they connect, and I was actually able to calculate it at the end. So this is related rates, guys. Step number one is always collect the data, information. Step number two, figure out geometry and formula. Step number three, differentiate using implicit differentiation. And then after that, good luck. Right? You plug everything in. Whatever you don't have, you have to go and hunt it down.
That sounds like something we should probably have written down.
So,
Get that again, please. We've not read that down already.
do what?
Write down through those rules for.
It's the procedure for each one of these problems, right? The first step was to identify all of the numbers that are given. And then step number two geometry and formula. And then in step number 3, we took the implicit derivative. And then step number 4, plug everything into the formula and calculate. Now there is sometimes step number 4 is different. Step number 4 would be to find additional calculations and variables, right, that you need. So there is no really concrete way to do this. It's gonna take practice, obviously, and I hope you guys will practice a lot. So this concludes chapter 3, and it concludes the material for your exam. We already had the first review yesterday. The notes of that will be posted. There was no stream because the network died. How is he doing now? Oh, he's doing great. Perfect. So we are going to have another review on Wednesday, tomorrow, right? Because you voted to have exam on Thursday. Quizzes are going. I hope you're enjoying those. And after the short break, we are going to start chapter 4. Bye.